My name is Amanda McCauley, and this is my Lab 4 presentation. The physics concepts behind this lab were circuits, loop rule, conservation of energy, conservation of current, and electric potential. The purpose of this lab was to characterize different circuits using the principles of energy and current conservation and analytical tools like ammeters and voltmeters. The first thing I did during this lab was predict the current of this circuit with two resistors in series and a battery, or two batteries. And using the loop rule, which comes from the conservation of energy, that this circuit round trip should have a change in electric potential of 0. So the battery minus the current times the additive resistance should be 0. And when I calculated this, I got my current to be 0.02 amps. And then when I used the simulation, I got the exact same value. And this didn't matter whether or not the ammeter was backwards or forwards. Then I closed the circuit with a voltmeter, and the change in potential was 3 volts, but the current was no longer flowing since the voltmeter had so much resistance in it. So there was still electric potential, but there was no current flowing. Then I measured the potential difference using the voltmeter across all these different points and plotted it from distance from the initial batteries. And it's notable that the round trip should be 0 volts in this idealized situation, and that the wires and the ammeters have no resistance, so the change in electric potential energy is 0, and that the voltage decreases as the current goes through the resistors. And then I calculated the specific resistance for each of the resistors and the wire and the ammeter using the change in voltage that I found using the voltmeter and the current that's running through this circuit, which I showed on the first slide as being 0.02, and the wire and the ammeter in this situation both have a resistance of 0, which would not be like real life. Then in an RC circuit with a resistor and a capacitor, if it's an uncharged capacitor and a battery, or a charged capacitor, they behave in similar ways visually, because it starts out with a current and then the current decreases with time, as shown using a light bulb. And when I measured the time for a capacitor to charge and discharge using 2 different light bulbs, it was the same time to charge and discharge, but it depended on the magnitude of the resistance. And RC circuits have a time dependence. Like I said before, the current decreases with time, and starting from the loop rule, you can derive this logarithmic function to determine this time dependence. And the circuit I used was just one charged capacitor and 1 resistor, and every second stopped and measured the potential difference across the capacitor. So it started out with 9 volts because it had been charged with a 9-volt battery, and then as time went by, the change in voltage decreased as the charge that was built up on the capacitors began to flow. And when this is plotted, the ln of the change in voltage over the initial change, you get a linear line with the slope being 1 over RC, which is called the time constant. And in my experiment, I measured the time constant to be 7.94. In conclusion, if this was in real life and used a real ammeter, the real ammeter would have had a small amount of resistance, and it wouldn't be the idealized change in voltage of 0 volts, and the round trip wouldn't have been 0. And this is a very similar answer to if it was using a real battery to charge a real capacitor. The prediction of the time expected to reach full charge using the equation that I did on the last slide, this prediction would be less than the real time value for the capacitor to reach full charge due to the additional resistance and value in the wires that we are not dealing with in this ideal simulation.